Deep within the fabric of our universe, there is a limit, a place where the very ideas of here and there begin to crumble. This is the Planck length. It is not just small, it is the smallest thing that smallness can be. Beyond it, the universe does not simply get tinier. Beyond it, space itself stops making sense. Distance loses meaning. Time fractures. The laws of physics, those reliable guides that have carried us from the surface of Earth to the edge of the observable cosmos, simply give up. They throw their hands in the air and admit defeat. And tonight, we are going to explore this boundary. We are going to journey to the very edge of what can be measured, what can be known, and what can even exist. So settle in. Let the world outside fade away and prepare to shrink down to a scale so small that reality itself begins to dissolve. Before we go any further, if you enjoy these journeys to the edges of understanding, consider liking this video and subscribing to Cosmic Drift. It helps us keep exploring the universe together, one quiet mystery at a time. Now, let us begin our descent. Think about yourself, sitting where you are right now. You are made of flesh and bone, of organs and tissue. But zoom in a little closer. Your skin is not a smooth surface. It is a landscape of cells, millions upon millions of them, each one a tiny factory of life. Zoom in further. Those cells are made of molecules. Water molecules, protein molecules, fat molecules, complex chains of atoms linked together in intricate patterns. Go deeper still. Those molecules are made of atoms, carbon, hydrogen, oxygen, nitrogen, the basic building blocks of everything you are. An atom is incredibly small. If you lined up 100 million of them side by side, they would stretch about 1 centimeter. That is roughly the width of your pinky fingernail. 100 million atoms, just across a fingernail. But we are not stopping at atoms. Atoms themselves are mostly empty space. At the center of each atom is a nucleus, a dense core made of protons and neutrons. And orbiting that nucleus in a fuzzy cloud of probability are electrons. The nucleus is tiny compared to the atom as a whole. If an atom were the size of a football stadium, the nucleus would be a marble sitting at the center of the field. Everything else is just emptiness, vast, echoing emptiness. But that marble, that nucleus, is where most of the atom's mass lives. And it is our next stop. Zoom in on the nucleus. Those protons and neutrons packed tightly together are not fundamental particles. They are made of something smaller. Quarks. 3 quarks make up each proton. 3 quarks make up each neutron. Quarks are held together by particles called gluons, which carry the strong nuclear force. This is the force that keeps the nucleus from flying apart. Despite the fact that protons, all positively charged, should repel each other. The strong force is powerful. It is the strongest force in nature. But it only works at incredibly short distances. At the scale of the nucleus, it is king. Beyond that, it fades to nothing. Quarks are strange. They have never been observed in isolation. You cannot pluck a single quark out of a proton and hold it up to the light. If you try to pull quarks apart, the energy you put in creates new quarks. They pop into existence in pairs, and you end up with more particles than you started with. Quarks are forever bound together, prisoners of the strong force. But they are also incredibly small. A quark is less than 10 to the power of negative 18 meters across. That is a decimal point followed by 17 zeros and then a 1. It is a billionth of a meter. At this scale, our everyday intuitions are useless. We have left the world of things we can see or touch or even imagine in any concrete way. But we are still not at the bottom, because the question remains, what happens if we keep going? What happens if we zoom in past the quarks, past the electrons, past every particle we have ever detected? Is there another layer, another set of smaller things hiding inside? Or is there a floor, a final level where the zooming stops? This is where the Planck length enters the story. And it is not just another small distance. It is the distance where the concept of distance itself begins to break down. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. Let that sink in for a moment. Negative 35. That is a decimal point, followed by 34 zeros, and then a 1 and a 6. It is so small that it makes a quark look enormous. It makes an atom look like a galaxy. To put it in perspective, the Planck length is to a grain of sand what a grain of sand is to the entire observable universe. Actually, that is not quite right. The Planck length is even smaller than that. Let us try some comparisons to really grasp this. An atom is about 10 to the power of negative 10 meters across. The Planck length is 10 to the power of negative 35 meters. That means the Planck length is 10 to the power of 25 times smaller than an atom. That is 10 million billion times smaller. If you could somehow shrink an atom down to the size of the observable universe, which is about 93 billion light years across, the Planck length would be about the size of an average tree. A tree in a universe-sized atom. That is the ratio we are talking about. Here is another way to think about it. A proton, one of those particles in the nucleus of an atom, is about 10 to the power of negative 15 meters across. The Planck length is about 10 to the power of 20 times smaller than a proton. That is 100 billion times smaller. If you took a proton and expanded it to the size of the observable universe, the Planck length would be about the size of a single human cell. Still incredibly tiny, even in a universe-sized proton. One more analogy. Let us say you have a dot on a piece of paper, a tiny dot, barely visible, about 0.1 millimeters across. Now, imagine you could scale that dot up to the size of the entire observable universe. 93 billion light years, a distance so vast that light, traveling at 300,000 kilometers per second, would take 93 billion years to cross it. If you scale that dot up to that size, the Planck length, in comparison, would still be about 0.1 millimeters, the same size as the original dot. That is how small the Planck length is. It is almost incomprehensibly tiny. But why does this length exist? Why is there a smallest possible distance? The answer lies in the fundamental constants of nature. There are a few numbers that show up everywhere in physics. The speed of light, which we call c, the gravitational constant, which we call g, and Planck's constant, which we call h. These numbers are not arbitrary. They are woven into the fabric of reality. They determine how light moves, how gravity pulls, how quantum mechanics operates. And when you combine these three constants in just the right way, you get the Planck length. The formula is relatively simple. You take Planck's constant, multiply it by the gravitational constant, divide by the speed of light cubed, and then take the square root. The result is the Planck length. It is a distance that emerges naturally from the laws of physics. It is not something we invented or chose. It is something the universe itself seems to define. And that makes it special. It suggests that at this scale, something fundamental is happening. Something that involves both quantum mechanics and gravity, the two great pillars of modern physics. Quantum mechanics is the science of the very small. It describes how particles behave, how they can be in multiple places at once, how they can tunnel through barriers, how they exist in states of probability until observed. It is strange and counterintuitive, but it works. It has been tested countless times and has never been proven wrong. Every piece of technology that relies on semiconductors, from your phone to your computer, is built on the principles of quantum mechanics. General relativity, on the other hand, is the science of the very large. It describes how gravity works, not as a force, but as a curvature of spacetime. Massive objects like stars and planets bend the fabric of space and time around them, and other objects move along those curves. It explains why planets orbit stars, why light bends around black holes, why time runs slower in strong gravitational fields. It too has been tested countless times and has never been proven wrong. Every GPS satellite in orbit has to account for the effects of general relativity, or it would give you the wrong location. But here is the problem. Quantum mechanics and general relativity do not play well together. They are both incredibly successful in their own domains, but when you try to combine them, the math breaks down. You get infinities, you get nonsense, you get predictions that make no sense. And nowhere is this problem more acute than at the Planck length, because at this scale, both quantum mechanics and gravity become equally important. You cannot ignore either one, and yet we do not have a theory that can handle both at once. This is one of the great unsolved problems in physics. We need a theory of quantum gravity, a theory that can describe what happens when quantum effects and gravitational effects are both strong. String theory is one attempt. Loop quantum gravity is another. There are others as well. But none of them have been proven. None of them have made predictions that we can test with current technology. We are still searching, still trying to understand what happens at the Planck scale. But even without a complete theory, we can make some educated guesses, and those guesses are strange, very strange. At the Planck length, space itself might not be smooth, it might not be continuous, it might be grainy, chunky, pixelated, like a digital image when you zoom in too far and start to see the individual pixels. This idea is sometimes called the quantum foam, and it suggests that at the smallest scales, space and time are not the calm, stable stage on which events unfold. They are dynamic, chaotic, bubbling with energy. The concept of quantum foam was first proposed by the physicist John Wheeler in the 1950s. Wheeler was a giant in the field of physics. He worked on the Manhattan Project. He coined the term black hole. He mentored Richard Feynman and Kip Thorne, and he had a deep intuition for the strange nature of quantum mechanics. Wheeler realized that if you apply the principles of quantum mechanics to space itself, you get something bizarre. At very small scales, space should be filled with fluctuations, tiny ripples and bubbles, virtual particles popping into and out of existence, a seething, frothing foam of energy. Here is how it works. In quantum mechanics, there is a principle called the Heisenberg uncertainty principle. It says that you cannot know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you know the other. But there is another version of this principle that applies to energy and time. It says that over very short periods of time, energy can fluctuate wildly. The universe can borrow energy as long as it pays it back quickly enough. And the shorter the time period, the larger the energy fluctuation can be. At the Planck scale, these fluctuations become enormous. The energy density becomes so high that it warps space-time itself. Tiny black holes might form and evaporate in an instant. Wormholes might open and close. The very geometry of space might twist and writhe. This is the quantum foam, a roiling, turbulent sea of space-time, where the smooth fabric we experience in everyday life dissolves into chaos. Of course, we have never seen the quantum foam. We have never directly observed the Planck length. And there is a good reason for that. It is not just that the Planck length is small. It is that it is fundamentally impossible to measure with any conceivable technology. To see why, we need to understand how we measure small things in the first place. When you look at something, you are detecting light that has bounced off it. Light is a wave, and waves have a wavelength. The wavelength determines the size of the smallest thing you can see. If you try to look at something smaller than the wavelength of the light you are using, the light just diffracts around it. It is like trying to catch a tiny fish with a net that has large holes. The fish just slips through. To see smaller things, you need light with a shorter wavelength. And shorter wavelength means higher energy. This is why electron microscopes can see smaller things than optical microscopes. Electrons, when they are moving fast, have a very short wavelength, much shorter than visible light, so they can resolve much finer details. But there is a limit to this process, because as you increase the energy of your probe, whether it is light or electrons or anything else, you start to affect the thing you are trying to measure. At some point, you put so much energy into such a small space that you create a black hole. And once you have created a black hole, you cannot see what is inside it. The black hole itself becomes the thing you are measuring, not the tiny structure you were trying to observe. This happens right around the Planck length. To probe distances at the Planck scale, you would need light with a wavelength of about the Planck length, and that light would have an energy of about the Planck energy, which is roughly 10 to the power of 9 joules. That might not sound like much. It is about the energy in a tank of gasoline. But remember, this energy is concentrated in a region the size of the Planck length. The energy density is unimaginably high, high enough to create a tiny black hole. So the very act of trying to measure the Planck length destroys the measurement. It is a fundamental limit, not just a technological one. This is one of the reasons why the Planck length is so significant. It is not just the smallest distance we can measure. It is the smallest distance that has any meaning. Below the Planck length, the concept of distance itself might not make sense. Space might not exist in any way we can understand. It is a boundary, a horizon beyond which our current physics cannot go. But let us step back for a moment and talk about the man who discovered the constant that bears his name. Max Planck. He was born in 1858 in Kiel, Germany. He came from a family of scholars. His father was a law professor. His grandfather and great-grandfather were theologians. Planck himself was drawn to physics, though his teachers tried to discourage him. One of his professors told him that physics was essentially complete, that all the important discoveries had already been made. There was nothing left to do but fill in a few decimal places. Planck ignored this advice, and it is a good thing he did. In the late 1890s, Planck was working on a problem that had stumped physicists for years. It was called the black body radiation problem. A black body is an idealized object that absorbs all the light that hits it and emits light based only on its temperature. Real objects, like a piece of hot metal or a star, approximate black bodies. The question was, how does the intensity of the light emitted by a black body depend on its wavelength and temperature? Experiments had been done. The data was clear, but no one could come up with a theory that matched the data. The problem was that the classical theories of the time predicted something called the ultraviolet catastrophe. According to classical physics, a black body should emit an infinite amount of energy at short wavelengths. Obviously, this did not happen in reality. Something was wrong with the theory. Planck tried various approaches. He tried to tweak the classical formulas. He tried different assumptions. Nothing worked. Finally, in a desperate move, he tried something radical. He assumed that energy was not continuous. He assumed that it came in discrete chunks, little packets that he called quanta. The size of each quantum was proportional to the frequency of the light, and the proportionality constant was a new fundamental constant, Planck's constant. With this assumption, Planck was able to derive a formula that perfectly matched the experimental data. He announced his result in December of 1900. It was a triumph. But Planck himself was not entirely comfortable with it. He thought of the quantization as a mathematical trick, not a real feature of nature. He spent years trying to find a way to derive his formula without assuming that energy came in chunks. He never succeeded, because energy really does come in chunks. Planck had discovered one of the foundational principles of quantum mechanics, even though he did not fully realize it at the time. Planck's constant, usually written as h, is a tiny number, about 6.6 times 10 to the power of negative 34 joule seconds. It shows up everywhere in quantum mechanics. It determines the energy of a photon. It sets the scale for the uncertainty principle. It defines the relationship between a particle's wavelength and its momentum. And when you combine it with the speed of light and the gravitational constant, it gives you the Planck length. Planck himself realized this. In the early 1900s, he proposed a system of natural units based on fundamental constants. The Planck length, the Planck time, the Planck mass, the Planck energy. These are not arbitrary human inventions like meters or seconds. They are defined by the universe itself. Planck received the Nobel Prize in Physics in 1918 for his work on quantum theory. He continued to work and teach for many years. He lived through both world wars. His son was executed by the Nazis for his involvement in a plot to assassinate Hitler. Planck himself remained in Germany throughout the war, a controversial decision that some criticized. He died in 1947, at the age of 89. But his legacy lives on. His constant is one of the most important numbers in physics, and the length scale that bears his name represents the ultimate frontier of our understanding. So what does it mean for space to be quantized? What does it mean for there to be a smallest possible distance? One way to think about it is to compare space to a digital image. When you look at a photograph on a screen, it looks smooth and continuous. But if you zoom in far enough, you start to see pixels, little squares of color. The image is not really continuous. It is made up of discrete units. Maybe space is the same way. Maybe if you could zoom in far enough, you would see that space is not smooth. It is made up of tiny cells, each one about a Planck length across. You could not have half a cell. You could not have a quarter of a cell. Space would come in indivisible units. This idea has profound implications. For one thing, it would mean that there is a limit to how much information you can pack into a region of space. Each Planck-sized cell could hold a certain amount of information, and that would be it. You could not subdivide further. This connects to ideas in black hole thermodynamics and the holographic principle, which suggests that the information content of a region of space is proportional to its surface area, not its volume. But that is a topic for another time. Another implication is that motion itself might be quantized. If space comes in discrete chunks, then moving from one place to another might be like moving from one pixel to another. You would not smoothly glide, you would jump. Of course, these jumps would be incredibly tiny, at the Planck scale, so in everyday life motion would still appear smooth, but at the deepest level, it might be fundamentally discontinuous. This is a strange thought. It challenges our intuition about what motion is, but quantum mechanics is full of strange thoughts that turn out to be true. There is also the question of what happens between the pixels. If space is made up of discrete cells, what is in the gaps? Is there anything there at all? Or is the question itself meaningless? Some theories suggest that space is not fundamental, that it emerges from something deeper, something that does not have the properties of space as we know it. In these theories, asking what is between the Planck cells is like asking what is north of the North Pole. The question does not make sense because you have reached the limit of the concept. Loop quantum gravity is one theory that takes this idea seriously. It proposes that space is made up of tiny loops, woven together into a network. The loops themselves are about a Planck length in size. The geometry of space emerges from the way these loops connect to each other. In this picture, space is not a smooth continuum. It is a discrete structure, like a fabric woven from threads. And just as a fabric looks smooth from a distance, but reveals its woven nature up close, space looks smooth at large scales, but becomes grainy at the Planck scale. String theory takes a different approach. It suggests that the fundamental objects in the universe are not particles, but tiny strings. These strings vibrate, and the different modes of vibration correspond to different particles. An electron is one mode, a quark is another, a photon is yet another. The strings themselves are about a Planck length long. In string theory, space might still be continuous, but the strings introduce a natural cutoff at the Planck scale. You cannot probe distances smaller than the size of a string, because the string itself is the fundamental object. Asking what happens inside a string is like asking what is inside a point. The question does not apply. Both of these theories are attempts to reconcile quantum mechanics and general relativity. Both suggest that something strange happens at the Planck scale, but neither has been proven. We do not have experimental evidence that can distinguish between them, or rule them out, or confirm them. We are still in the realm of speculation. Educated speculation based on deep mathematical reasoning, but speculation nonetheless. One of the challenges is that the Planck scale is so far removed from anything we can directly observe. The Large Hadron Collider, the most powerful particle accelerator ever built, can probe distances down to about 10 to the power of -19 meters. That is incredibly small. It is small enough to see the internal structure of protons. It is small enough to discover the Higgs boson, but it is still about 10,000 trillion times larger than the Planck length. To build an accelerator that could probe the Planck scale, you would need a machine the size of the galaxy, maybe larger. It is not going to happen anytime soon. So we are left with indirect evidence. We look for subtle effects that might hint at Planck scale physics. We look at the cosmic microwave background, the afterglow of the Big Bang, to see if there are any anomalies that could be explained by quantum gravity. We study black holes, where gravity is strong and quantum effects might be important. We look at the behavior of particles at the highest energies we can achieve. We build mathematical models and see if they make predictions that we can test. It is slow work. It is painstaking work, but it is the only way forward. There is also a philosophical dimension to the Planck length. It forces us to confront the limits of knowledge. There are things we can never know, not because we lack the technology, but because the universe itself forbids it. The Planck length is a boundary. Beyond it, our concepts break down. Distance, time, causality. These are the tools we use to make sense of the world. But at the Planck scale, they might not apply. We might need entirely new concepts, new ways of thinking, new language. And that is both humbling and exciting. Humbling because it reminds us that we are not all-knowing, that the universe is deeper and stranger than we can imagine, that there are mysteries we may never solve. But exciting because it means there is always more to discover, always another layer, always another question. The Planck length is not the end of physics. It is a signpost pointing towards something beyond, something we do not yet understand. And that is what drives science forward. The desire to know, the curiosity to explore, the willingness to admit ignorance and then work to overcome it. Let us return to the quantum foam for a moment. This idea that space at the Planck scale is not smooth, but turbulent. What would it actually look like if you could somehow see it? Of course you cannot. We have established that. But let us use our imagination. Picture the surface of the ocean. From an airplane, it looks smooth. A vast expanse of blue. But get closer, and you see waves. Get closer still, and you see ripples and foam. Get right down to the surface, and you see a chaotic churning mess. Water splashing, bubbles forming and popping, spray flying. The ocean is not smooth at all. It is dynamic and complex. Now imagine that space is like that. At large scales, it looks smooth, calm, predictable. But zoom into the Planck scale, and it becomes a seething foam. Virtual particles appear and disappear. Tiny black holes form and evaporate. The geometry of space itself fluctuates wildly. There is no stable background, no fixed stage. Everything is in flux. This is the quantum foam. And it is not just a metaphor. It is a prediction that comes out of trying to apply quantum mechanics to gravity. Virtual particles are a key part of this picture. In quantum mechanics, the vacuum is not empty. It is full of energy. Pairs of particles and antiparticles constantly pop into existence, exist for a brief moment, and then annihilate each other. This happens everywhere, all the time. But normally, these virtual particles exist for such a short time and have such low energy that they do not have much effect. They are like fleeting shadows. But at the Planck scale, the energy of these fluctuations becomes enormous. The virtual particles become real, in a sense. They warp spacetime. They create the foam. This has been tested, in a way. There is an effect called the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force. This force comes from the virtual particles in the vacuum. The space between the plates can only support certain wavelengths of virtual particles, while the space outside can support all wavelengths. This creates a pressure difference, and the plates are pushed together. The Casimir effect has been measured in the lab. It is real, and it is a direct consequence of the quantum vacuum being full of energy. So while we cannot see the quantum foam directly, we have evidence that the vacuum is not empty, that it is seething with activity. Another consequence of the Planck length is that it sets a limit on how finely we can divide time. Just as there is a smallest meaningful distance, there is a smallest meaningful duration. This is called the Planck time. It is the time it takes light to travel one Planck length, and it is about 5.4 times 10 to the power of negative 44 seconds. That is a decimal point, followed by 43 zeros, and then a 5 and a 4. It is unimaginably short. In 1 second, there are about 10 to the power of 44 Planck times. That is more Planck times in 1 second than there are seconds in the age of the universe, multiplied by 1 trillion. What does it mean for there to be a smallest unit of time? It means that time, like space, might be quantized. It might come in discrete ticks, like the frames of a movie. Each frame lasts 1 Planck time, and between the frames, there is nothing. No time passes. The universe jumps from one frame to the next. Of course, these jumps are so fast that we would never notice. Time would still appear smooth and continuous. But at the deepest level, it might be fundamentally discrete. This has implications for causality. Causality is the idea that cause precedes effect, that events happen in a sequence. But if time is quantized, then the notion of before and after becomes fuzzy at the Planck scale. Two events that happen within 1 Planck time of each other might not have a well-defined order. It might not make sense to ask which came first. This is deeply strange. It challenges our basic understanding of how the universe works. But it is a logical consequence of taking the Planck scale seriously. There is also the Planck mass. This is the mass of a particle whose Compton wavelength is equal to the Planck length. The Compton wavelength is a quantum mechanical property that relates a particle's mass to a length scale. For a particle with the Planck mass, this length scale is the Planck length. The Planck mass is about 2.2 times 10 to the power of -8 kilograms. That is about the mass of a flea egg. It might not sound like much, but remember, this is the mass of a single particle. A particle with the Planck mass would be incredibly dense. If you compressed it down to the Planck length, it would form a black hole. In fact, the Planck mass is sometimes defined as the mass of a black hole whose Schwarzschild radius is equal to the Planck length. The Planck energy is the energy equivalent of the Planck mass. Using Einstein's famous equation, energy equals mass times the speed of light squared. The Planck energy is about 2 billion joules. That is roughly the energy released by a car traveling at highway speed, or the energy in a lightning bolt, or the energy needed to power a typical house for a few weeks. Again, this might not sound like much on a human scale, but remember, this is the energy of a single particle. A particle with the Planck energy would be extraordinarily energetic. If such a particle existed, it would be a tiny, incredibly dense, incredibly hot speck, and it would probably decay or interact almost immediately. These Planck units are not just curiosities. They represent natural scales for the universe. They are the scales at which quantum mechanics and gravity are equally important. They are the scales at which our current theories break down, and they are the scales at which new physics must emerge. Whatever theory of quantum gravity we eventually discover, it will have to explain what happens at the Planck scale. It will have to tell us what space and time really are. It will have to reconcile the smooth, continuous space-time of general relativity with the discrete, probabilistic world of quantum mechanics. One of the most intriguing ideas to come out of Planck scale physics is the holographic principle. This principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. It is like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. The holographic principle was inspired by the study of black holes. Stephen Hawking and Jacob Bekenstein showed that the entropy of a black hole, which is a measure of its information content, is proportional to the area of its event horizon, not its volume. This was surprising. You would expect the information content to scale with volume, but it scales with area. This led to the idea that maybe space itself is holographic, that the three-dimensional world we experience is actually encoded on a two-dimensional surface, and the fundamental units of this encoding are Planck-sized. Each Planck area on the surface corresponds to one bit of information. This is a radical idea. It suggests that space is not fundamental, that it is an emergent phenomenon, like temperature or pressure. Temperature is not a fundamental property of atoms. It is a statistical property that emerges when you have many atoms. Maybe space is the same way. Maybe it emerges from something deeper, something that does not have spatial properties. The holographic principle has been explored in the context of string theory, particularly in something called the ADS-CFT correspondence. This is a mathematical relationship between a theory of gravity in a higher dimensional space and a quantum field theory on the boundary of that space. It is a concrete realization of the holographic principle, and it has been incredibly fruitful for theoretical physics. It has led to new insights into black holes, quantum entanglement, and the nature of spacetime itself. But it is still a work in progress. We do not yet have a complete holographic description of our universe. Another idea that connects to the Planck scale is the concept of emergent spacetime. This is the idea that space and time are not fundamental ingredients of reality, but rather they emerge from something more basic. Just as the wetness of water emerges from the interactions of water molecules, spacetime might emerge from the interactions of more fundamental entities. What those entities are, we do not know. They might be loops, as in loop quantum gravity. They might be strings, as in string theory. They might be something else entirely. But the key point is that spacetime is not the starting point. It is the result. This is a profound shift in perspective. For centuries, we have thought of space and time as the stage on which the universe plays out. They are the background, the container, the arena. But if space-time is emergent, then it is part of the play, not the stage. It is something that arises from the interactions of the actors. And at the Planck scale, where those interactions are strongest, space-time might not exist in any recognizable form. It might be replaced by something entirely different, something we do not yet have the concepts to describe. This brings us to one of the deepest questions in physics. What is the universe made of? At the most fundamental level, what are the basic ingredients? For a long time, we thought it was atoms. Then we discovered that atoms are made of protons, neutrons, and electrons. Then we discovered that protons and neutrons are made of quarks. We found more particles, neutrinos, muons, gluons, photons, the Higgs boson. We built the standard model of particle physics, which describes all the known particles and how they interact. It is one of the most successful theories in the history of science. But it is not complete. It does not include gravity. It does not explain dark matter or dark energy. And it does not tell us what happens at the Planck scale. Maybe the answer is that there are no fundamental particles. Maybe everything is made of strings or loops or some other structure. Or maybe the question itself is wrong. Maybe asking what the universe is made of is like asking what a symphony is made of. You could say it is made of sound waves. Or you could say it is made of notes. Or you could say it is made of the intentions of the composer. All of these answers are true in some sense, but none of them captures the full picture. Maybe the universe is like that. Maybe it is not made of things at all, but of relationships, processes, patterns. Maybe the Planck scale is where we finally have to let go of our intuition about objects and embrace a more abstract, more mathematical understanding of reality. Let us talk about black holes for a moment, because they are intimately connected to the Planck scale. A black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon. Once you cross the event horizon, you are doomed. You will be pulled inexorably toward the center, toward the singularity. The singularity is a point where the curvature of spacetime becomes infinite, where the density becomes infinite, where the laws of physics, as we know them, break down. But here is the thing. We do not really believe that the singularity is a point of infinite density. We think that is a sign that our theory is incomplete. General relativity predicts the singularity, but general relativity does not include quantum mechanics. And at the center of a black hole, where the gravitational field is incredibly strong and the region is incredibly small, quantum effects must be important. We need a theory of quantum gravity to describe what really happens at the singularity. And that theory will almost certainly involve the Planck scale. One possibility is that the singularity is not a point, but a region about a Planck length across. Inside that region, spacetime is so warped and quantum fluctuations are so strong that the classical notion of a singularity does not apply. Instead, you have a quantum foam, a chaotic mess of spacetime geometry. Or maybe the singularity is replaced by something else entirely, a bounce, where the collapsing matter rebounds and creates a new region of spacetime. Or a wormhole, connecting the black hole to another part of the universe, or even to another universe. These are speculative ideas, but they are grounded in serious attempts to understand quantum gravity. Black holes also have a temperature. This was discovered by Stephen Hawking in the 1970s. He showed that black holes emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. The temperature of a black hole is inversely proportional to its mass. A large black hole has a very low temperature. A small black hole has a high temperature. And a black hole with a mass equal to the Planck mass would have a temperature equal to the Planck temperature, which is about 10 to the power of 32 Kelvin. That is unimaginably hot. It is the temperature at which the thermal energy is equal to the Planck energy. At the Planck temperature, the distinction between particles and spacetime breaks down. The thermal fluctuations are so strong that they create and destroy black holes. They warp spacetime on the Planck scale. It is a regime where quantum gravity is essential, and it is a regime that existed in the very early universe, right after the Big Bang, which brings us to the connection between the smallest thing and the biggest thing, between the Planck length and the cosmos. The Big Bang is the event that started our universe. About 13.8 billion years ago, the universe was incredibly hot, incredibly dense, and incredibly small. It has been expanding and cooling ever since. We have a lot of evidence for the Big Bang. The cosmic microwave background, the abundance of light elements, the large-scale structure of the universe. All of these point to a hot, dense beginning. But the Big Bang theory, as it is usually formulated, does not tell us what happened at the very beginning. It does not tell us what happened in the first moments, because in the first moments, the universe was so small and so dense that quantum gravity was important, and we do not have a theory of quantum gravity. There is a specific moment in the early universe called the Planck epoch. This is the period from time 0 to about 1 Planck time, which is about 10 to the power of negative 43 seconds after the Big Bang. During the Planck epoch, the entire observable universe was smaller than the Planck length. The temperature was at the Planck temperature. The density was at the Planck density, which is about 10 to the power of 96 kilograms per cubic meter. That is a 1 followed by 96 zeros. It is so dense that a single cubic centimeter would contain more mass than the entire observable universe does today. At the Planck epoch, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all unified into a single force. There was no distinction between them. Particles and spacetime were indistinguishable. The universe was a quantum foam, a seething, chaotic mess of energy and geometry. We cannot describe what happened during the Planck epoch with our current theories. General relativity breaks down. The standard model breaks down. We need quantum gravity, and we do not have it. But after the Planck epoch, things start to make sense. The universe expanded and cooled. The forces began to separate. First gravity split off, then the strong nuclear force, then the weak nuclear force and electromagnetism. Particles began to form, quarks and gluons, then protons and neutrons, then atomic nuclei, then atoms, then stars and galaxies. The universe evolved from a hot, dense, uniform state to the rich, complex cosmos we see today. And all of that happened after the Planck epoch. The Planck epoch is the boundary of our knowledge. It is the moment before which we cannot see. This is both frustrating and fascinating. Frustrating because we want to know what happened. We want to understand the very beginning. But fascinating because it means there is a deep mystery at the heart of existence. The universe came from somewhere. It had a beginning, and that beginning is hidden behind the Planck scale. It is a veil we cannot yet lift, but maybe someday we will. Maybe a future theory of quantum gravity will let us peer into the Planck epoch. Maybe we will understand how the universe was born. Or maybe the question itself will turn out to be wrong. Maybe time itself began at the Planck epoch, and asking what came before is like asking what is north of the North Pole. We do not know, and that is okay. Not knowing is the starting point for discovery. There is something poetic about the connection between the smallest and the largest. The Planck length, the tiniest distance imaginable, is the size the entire universe once was. Everything that exists, every star, every galaxy, every atom in your body was once compressed into a region smaller than a Planck length. It is almost impossible to wrap your mind around, but it is what the evidence suggests, and it means that the Planck scale is not just an abstract curiosity. It is intimately connected to the story of the cosmos. It is part of our origin story. Let us think about what it means for the universe to have been that small. At the Planck scale, the concepts of space and time break down. So in some sense, it does not even make sense to say the universe was small. Small compared to what? There was no outside. There was no before. There was just this tiny, dense, hot region, and it was everything. And then it began to expand. Space itself expanded. Not into anything, just expanded. And as it expanded, it cooled. And as it cooled, structure began to form. The universe went from a featureless soup to a cosmos full of stars and planets and life. This expansion is still happening. The universe is still growing. Galaxies are moving away from each other. The farther away a galaxy is, the faster it is receding. This is not because the galaxies are moving through space. It is because space itself is expanding, and the expansion is accelerating. Something called dark energy is pushing the universe apart, faster and faster. We do not know what dark energy is. It is one of the biggest mysteries in cosmology, but we can measure its effects, and those effects tell us that the universe will continue to expand forever. It will grow colder and emptier. Stars will burn out. Black holes will evaporate. Eventually, the universe will be a vast, dark, cold expanse. with nothing but the faint glow of Hawking radiation from the last black holes. And then even that will fade. The universe will reach a state of maximum entropy where nothing interesting can happen anymore. This is called the heat death of the universe. It is trillions upon trillions of years in the future, but it is the ultimate fate predicted by our current understanding. But let us not get too gloomy. We are here now. The universe is young and vibrant. Stars are being born. Planets are forming. Life is evolving. And we, improbable collections of atoms, are able to look out at the cosmos and wonder. We are able to ask questions about the Planck length and the Big Bang and the nature of reality. That is extraordinary. It is a privilege, and it is a responsibility, because we are the universe trying to understand itself. We are the cosmos waking up and looking in the mirror. The Planck length reminds us of our limits. It reminds us that there are things we do not know, things we may never know. But it also reminds us of our potential, because even though we cannot see the Planck length, we can deduce its existence. We can calculate its value. We can reason about what it means. We can build theories that incorporate it. We can push the boundaries of knowledge, even if we cannot cross them. That is the power of science. That is the power of human curiosity. There is also a humility in confronting the Planck scale. It is easy to think of ourselves as the center of the universe. We are big. We are important. We matter. And in a sense, that is true. We do matter. But the Planck length puts things in perspective. We are not at the center of the scale of the universe. We are somewhere in the middle. There are things much larger than us, galaxies, superclusters, the observable universe itself. And there are things much smaller than us, atoms, protons, quarks, the Planck length. We are just one scale among many, and that is okay. It does not diminish us. It situates us. It gives us context. And yet, despite being in the middle, we are able to comprehend both ends. We can think about the Planck length. We can think about the size of the universe. We can hold both in our minds at once. That is remarkable. It is a testament to the power of abstraction, of mathematics, of imagination. We are not limited by our size. We are not limited by our senses. We can reach beyond ourselves in both directions and grasp the very large and the very small. Let us consider some of the practical implications of Planck scale physics. Even though we cannot directly observe the Planck length, it might have subtle effects that we can detect. For example, some theories of quantum gravity predict that the speed of light might depend slightly on its energy. High-energy photons might travel slightly faster or slower than low-energy photons. This effect would be incredibly tiny. But over vast distances, like the distance from a distant gamma-ray burst to Earth, it might add up to a measurable difference. Astronomers have looked for this effect. So far, they have not found it, but the search continues. If we ever do detect such an effect, it would be a smoking gun for quantum gravity. It would be direct evidence that spacetime is not smooth at the Planck scale. Another potential effect is in the cosmic microwave background. This is the afterglow of the Big Bang, a faint glow of microwave radiation that fills the entire sky. It is incredibly uniform, but not perfectly so. There are tiny fluctuations, tiny differences in temperature from one part of the sky to another. These fluctuations are the seeds of all the structure in the universe. They are the reason we have galaxies and stars and planets. The fluctuations were created by quantum fluctuations in the very early universe, during a period called inflation. Inflation is a theory that says the universe underwent a brief period of incredibly rapid expansion, right after the Planck epoch. This expansion stretched tiny quantum fluctuations to cosmic scales, and those fluctuations became the seeds of structure. If inflation is correct, and most cosmologists think it is, then the cosmic microwave background carries information about the Planck scale. The fluctuations we see today were once Planck-sized quantum fluctuations. By studying the cosmic microwave background in exquisite detail, we might be able to learn something about quantum gravity. We might be able to see the fingerprints of the Planck scale imprinted on the sky. This is one of the reasons why cosmologists are so interested in measuring the cosmic microwave background with ever greater precision. It is a window into the very early universe. It is a window into the Planck epoch. There are also implications for the nature of information. If space is quantized, if it comes in Planck-sized chunks, then there is a limit to how much information you can store in a given volume. Each Planck volume can hold a certain amount of information, and that is it. This has led to ideas about the universe as a kind of computer. A vast cosmic computer, where the Planck scale structure is the hardware and the laws of physics are the software. This is a speculative idea, but it is taken seriously by some physicists. It connects to ideas in computer science, information theory, and the foundations of quantum mechanics. One of the most famous proponents of this view was John Wheeler, the same physicist who proposed the quantum foam. Wheeler had a slogan, "It from bit." He believed that information, not matter or energy, was the fundamental stuff of the universe, that everything, every particle, every force, every aspect of reality ultimately comes down to information, to bits, ones and zeros, and the Planck scale is where this information is encoded, where the bits live. This is a radical idea. It turns our usual picture upside down. Instead of information being something that describes matter, matter is something that emerges from information. It is a shift from a materialist view to an informational view, and it is still being explored and debated. Let us also think about the philosophical implications. The Planck length challenges our notions of infinity. In mathematics, you can always divide a number in half. You can keep dividing forever. There is no smallest number. But in physics, there might be a smallest distance. The Planck length might be the end of the line. You cannot go smaller. This suggests that the physical world is fundamentally different from the mathematical world. Mathematics is continuous. Physics might be discrete. This has implications for how we think about the relationship between math and reality. Is math just a tool we use to describe reality? Or is reality itself mathematical? If the Planck length is real, it suggests that reality has a structure that math can describe, but that reality is not identical to math. There are physical constraints that go beyond pure mathematics. There is also the question of determinism. In classical physics, if you know the state of a system at one time, you can predict its state at any future time. The universe is like a clockwork. Everything is determined. But quantum mechanics introduces randomness. The outcome of a quantum measurement is not determined. It is probabilistic. And at the Planck scale, where quantum effects are dominant, this randomness is fundamental. It is not just that we do not know what will happen. It is that what will happen is not determined until it happens. This has profound implications for free will, for causality, for the nature of time. If the universe is fundamentally random at the smallest scales, then the future is not written. It is open. It is being created moment by moment. Of course, this does not mean that anything can happen. The probabilities are constrained by the laws of physics. Quantum mechanics gives you precise rules for calculating the probabilities of different outcomes. But within those rules, there is genuine randomness. And that randomness might be the source of novelty in the universe. It might be why the universe is not a static, unchanging thing, but a dynamic, evolving cosmos. It might be why new things can emerge, why life can arise, why consciousness can develop. The Planck scale, with its quantum foam and its fundamental uncertainty, might be the wellspring of creativity in the universe. Let us return to the idea of the quantum foam one more time, because it is so central to understanding the Planck scale. The foam is not just a metaphor, it is a prediction. If you take the equations of quantum mechanics and apply them to space-time itself, you get a picture of space that is wildly fluctuating at the smallest scales. The geometry of space is not fixed. It is constantly changing. Tiny wormholes might open and close. Tiny regions of space might pinch off and reconnect. The topology of space, the way it is connected, might be in flux. This is very different from the smooth, static space-time of general relativity. It is a dynamic, living structure. One way to visualize this is to think of space-time as a fabric. At large scales, the fabric looks smooth and uniform. But zoom in, and you see that it is woven from threads. Zoom in further, and you see that the threads themselves are made of smaller fibers. Zoom in even further, and you reach the Planck scale, where the fibers are constantly moving, twisting, breaking, and reconnecting. The fabric is not static, it is alive. It is the quantum foam. And everything that exists, every particle, every force, is a pattern in this foam. A ripple, a wave, a knot. We are all patterns in the quantum foam. We are all part of the dance. This view has implications for the nature of particles. In quantum field theory, particles are excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. But if space-time itself is quantized, if it is made of discrete units, then maybe particles are not excitations of fields. Maybe they are topological features of space-time, knots or twists or loops in the fabric. This is the idea behind some approaches to quantum gravity, that particles are not separate from space-time. They are aspects of space-time. They are the way space-time is knotted or twisted at the Planck scale. This is a beautiful idea. It unifies matter and space. It says that there is only one thing, space-time, and everything else, all the particles and forces, are just different ways that space-time can be configured. It is a monistic view, as opposed to a dualistic view, where matter and space are separate. And it is deeply elegant, but it is also deeply challenging, because it requires us to rethink everything we know about particles and fields and forces. It requires a complete overhaul of our conceptual framework, and that is hard. It is hard to let go of ideas that have served us well for so long. But that is what progress requires. The willingness to question. The willingness to start over. There is also the question of whether the Planck length is truly fundamental, or whether it is just a marker, a signpost that says, "Here be dragons." Some physicists think that the Planck length is the absolute limit, that there is nothing smaller. That space is literally made of Planck-sized cells. Others think that the Planck length is just the scale at which our current theories break down, that there might be structure below the Planck scale, but we need a new theory to describe it. We do not know which view is correct. We do not have the evidence to decide, but it is an important question, because if there is structure below the Planck scale, then the Planck length is not the end of the story. It is just another layer, and the true fundamental scale might be even smaller. But even if the Planck length is not the absolute bottom, it is still incredibly significant. It is the scale at which quantum gravity becomes important. It is the scale at which our current theories fail. It is the boundary of our knowledge, and that makes it worth studying, worth thinking about, worth trying to understand, because understanding the boundary is the first step to crossing it. Let us think about the role of symmetry in all of this. Symmetry is a central concept in physics. A symmetry is a transformation that leaves something unchanged. For example, a circle has rotational symmetry. You can rotate it by any angle, and it still looks the same. The laws of physics have symmetries too. They are the same everywhere in space. They are the same at all times. They are the same for all observers moving at constant velocity. These symmetries are not arbitrary. They are deeply connected to the conservation laws. The symmetry of space leads to conservation of momentum. The symmetry of time leads to conservation of energy. The symmetry of rotation leads to conservation of angular momentum. At the Planck scale, some of these symmetries might break down. Space might not be the same everywhere. Time might not flow smoothly. The usual symmetries of spacetime might be replaced by something else. Some theories of quantum gravity, like string theory, introduce new symmetries. Supersymmetry, for example, is a symmetry that relates particles of different spin. It predicts that every particle has a superpartner. We have not found any superpartners yet, but the search continues. If supersymmetry is real, it might be a symmetry of the Planck scale. It might be a clue to the deeper structure of reality. There is also the idea of emergent symmetry. This is the idea that the symmetries we observe at large scales are not fundamental. They emerge from a more complex, less symmetric structure at small scales. Just as the smoothness of water emerges from the chaotic motion of water molecules, the symmetries of spacetime might emerge from the quantum foam. At the Planck scale, spacetime might be highly asymmetric, chaotic, disordered. But when you average over many Planck-sized regions, the chaos averages out, and you get the smooth, symmetric spacetime we observe. This is a powerful idea. It suggests that the order we see in the universe is not imposed from above. It is not a fundamental feature. It is an emergent property. It arises from the collective behavior of many tiny, chaotic components. Let us also consider the role of observation. In quantum mechanics, observation plays a crucial role. Before you measure a particle, it exists in a superposition of states. It is in multiple places at once, or has multiple values of momentum at once. But when you measure it, the superposition collapses. The particle takes on a definite value. This is called the measurement problem, and it is one of the deepest puzzles in quantum mechanics. What counts as a measurement? What causes the collapse? Is it the act of observation itself, or is it something else? At the Planck scale, the measurement problem becomes even more acute, because to measure something at the Planck scale, you need to interact with it. And any interaction at the Planck scale involves enormous energies high enough to create black holes. So the act of measurement fundamentally alters what you are trying to measure. You cannot observe the Planck scale without changing it. This is not just a practical limitation. It is a fundamental feature of reality. It suggests that at the Planck scale, the observer and the observed are not separate. They are entangled. They are part of the same system. And this has implications for the nature of reality itself. It suggests that reality is not something that exists independently of observation. It is something that is created, or at least shaped, by observation. This is a controversial idea. It challenges our intuition that the world exists whether we look at it or not. but it is a natural consequence of taking quantum mechanics seriously. And at the Planck scale, where quantum effects are dominant, it might be unavoidable. The universe at the Planck scale might not be a collection of objects with definite properties. It might be a web of relationships, a network of interactions, where nothing has a definite state until it interacts with something else. This is a relational view of reality, and it is very different from the classical view, where objects have definite properties independent of observation. There is also the question of what it means for something to exist. We usually think of existence as binary. Something either exists or it does not. But at the Planck scale, existence might be more nuanced. Virtual particles exist for a brief moment and then disappear. Do they really exist? Or are they just mathematical artifacts? Quantum fluctuations create and destroy tiny black holes. Do those black holes exist? Or are they just possibilities that never quite become real? The line between existence and non-existence might be blurry at the Planck scale. And that challenges our usual categories. It forces us to think more carefully about what we mean by existence. Let us think about the connection between the Planck scale and consciousness. This is highly speculative, but some physicists and philosophers have suggested that consciousness might be related to quantum processes in the brain. The idea is that the brain is not just a classical computer, it is a quantum computer. And the quantum processes that occur in neurons or in structures within neurons might be the basis of consciousness. If this is true, then the Planck scale might be relevant to understanding consciousness, because quantum processes are ultimately governed by Planck scale physics. This is a controversial idea. Most neuroscientists think that consciousness can be explained by classical processes in the brain, that you do not need quantum mechanics to understand how the brain works. But a few researchers, like Roger Penrose and Stuart Hameroff, have argued that quantum effects are essential. They have proposed that structures called microtubules, which are part of the cytoskeleton of neurons, might support quantum coherence, and that the collapse of quantum states in these microtubules might be the basis of conscious experience. This is called the Orchestrated Objective Reduction Theory, or ORC-OR. The theory is highly speculative and has been criticized on various grounds, but it is an interesting attempt to connect the quantum world to the world of mind. And if it is correct, then the Planck scale, as the fundamental scale of quantum gravity, might play a role in consciousness. This is a long shot, but it is worth thinking about, because consciousness is one of the great mysteries, and the Planck scale is another great mystery. Maybe they are connected. Maybe understanding one will help us understand the other. Let us return to the cosmos. We have talked about the Planck epoch, the first moment after the Big Bang. But what about before the Big Bang? Did anything exist before? Or is the Big Bang the absolute beginning? This is one of the most profound questions we can ask, and the answer depends on what happened at the Planck scale. If time itself began at the Big Bang, then asking what came before is meaningless. It is like asking what is north of the North Pole. There is no north of the North Pole. There is no before the Big Bang. Time started with the Big Bang, but some theories suggest that time did not begin at the Big Bang, that the Big Bang was not the beginning, but a transition, a bounce. In these theories, the universe existed before the Big Bang, but in a different state. Maybe it was contracting. Maybe it reached a minimum size, about the Planck length, and then bounced back, beginning the expansion we see today. This is called a bouncing cosmology. It avoids the singularity at the Big Bang. It replaces it with a smooth transition, and it suggests that the universe might be eternal, that it has always existed, going through cycles of expansion and contraction. Another possibility is that our universe is part of a multiverse, that the Big Bang was not the creation of everything but the creation of our particular universe, and that there are other universes with different laws of physics, different constants, different histories. These universes might have been created by other Big Bangs, or they might exist in parallel in a higher dimensional space. This is the multiverse hypothesis. It is highly speculative. We have no direct evidence for it, but it is a logical possibility, and it is taken seriously by some cosmologists. If the multiverse is real, then the Planck scale might be the scale at which universes are created. Quantum fluctuations at the Planck scale might spawn new universes, tiny bubbles of space-time that inflate and become full-fledged universes. This is called eternal inflation. It is a theory that combines inflation with the multiverse, and it suggests that the creation of universes is an ongoing process, that new universes are being born all the time, at the Planck scale, in the quantum foam. We would never see these other universes. They would be causally disconnected from us, but they would exist, and they would be part of the larger reality. These ideas are mind-bending. They challenge our notions of what is real, what is possible, what is knowable. But they are grounded in serious physics. They are attempts to make sense of the evidence, to push the boundaries of understanding, to explore the implications of our theories. And they all come back to the Planck scale, because the Planck scale is where the action is. It is where the universe was born. It is where new universes might be born. It is where the fundamental laws of physics are written. Let us think about the future of Planck scale physics. What will we learn in the coming decades? We are not going to build a Planck scale particle accelerator. That is not feasible. But we can look for indirect evidence. We can study the cosmic microwave background with greater precision. We can observe gravitational waves from the early universe. We can search for subtle effects in the behavior of particles at high energies. We can develop better theories and see if they make testable predictions. Progress will be slow, but it will happen, because that is how science works. One small step at a time. There are also new technologies on the horizon. Quantum computers might help us simulate Planck-scale physics. They might let us explore the quantum foam in ways that classical computers cannot. Gravitational wave detectors might become sensitive enough to detect the echoes of the Planck epoch. Space-based telescopes might see farther back in time, closer to the Big Bang. Each new tool, each new technique, brings us a little closer to understanding the Planck scale. And each new understanding brings us a little closer to a complete theory of quantum gravity. But even if we never fully understand the Planck scale, the journey is worthwhile, because the journey itself is what science is about. It is about asking questions. It is about exploring the unknown. It is about pushing the limits of what we can know. And the Planck scale is the ultimate limit. It is the edge of the map, the place where the dragons live. And that makes it irresistible. We cannot help but wonder, what is there? We cannot help but try to find out. There is also a sense in which the Planck scale is a mirror. It reflects back to us our own limitations. It shows us that we are finite beings trying to understand an infinite universe. It shows us that there are things we cannot see, cannot measure, cannot fully grasp. But it also shows us that we can still reason. We can still imagine. We can still build theories and test them and refine them. We can still make progress, even if we never reach the final answer. And that is a kind of triumph. It is a triumph of the human spirit, the refusal to accept ignorance, the determination to understand. let us also appreciate the beauty of the Planck scale. There is something elegant about the way it emerges from the fundamental constants, the speed of light, the gravitational constant, Planck's constant, three numbers that seem unrelated, but when combined give you a length, a time, a mass, an energy, a temperature, a complete set of natural units. It is as if the universe is telling us something. It is as if there is a hidden order, a deeper structure, waiting to be discovered. And the Planck scale is the key. It is the clue that will unlock the mystery. There is also beauty in the connections, the way the smallest thing connects to the largest thing, the way the Planck length connects to the Big Bang, the way quantum mechanics connects to gravity, the way space connects to time, the way matter connects to energy, the way information connects to reality. These connections are not obvious. They are not on the surface. You have to dig deep to find them. But when you do, they are breathtaking. They reveal a unity underlying the diversity, a simplicity underlying the complexity, a coherence underlying the chaos. And that is what physics is ultimately about. Finding the patterns, finding the connections, finding the underlying order. The Planck scale is a piece of that order. It is a thread in the tapestry, and by pulling on that thread, we might unravel the whole thing. We might see the full picture. We might understand how the universe works, from the smallest scale to the largest, from the beginning to the end, from the quantum foam to the cosmic web. But even if we do not, even if the Planck scale remains forever beyond our reach, it is still worth contemplating, because it reminds us of the grandeur of the universe. It reminds us that we are part of something vast and ancient and mysterious. It reminds us that there is always more to learn, always more to discover, always more to wonder about. And that is a gift. It is a gift to live in a universe that is not fully known, that is not fully understood, that still has secrets, that still has mysteries, that still has room for awe. So here we are, at the end of our journey. We have traveled from the everyday world down to the Planck length. We have explored the quantum foam. We have met Max Planck and learned about his discovery. We have thought about black holes and the Big Bang. We have considered the nature of space and time and reality itself, and we have confronted the limits of our knowledge, the boundary beyond which we cannot see, the horizon beyond which our theories break down. But we have also seen that this boundary is not a wall. It is a frontier. It is an invitation. It is a challenge. It is the universe saying, "Come and find me. Come and understand me. Come and explore." And we are answering that call. We are building theories. We are making observations. We are asking questions. We are pushing forward, because that is what we do. That is what it means to be human, to wonder, to explore, to seek. The Planck length is where space itself stops making sense, but it is also where our understanding begins. It is the starting point for a new physics, a physics that can handle both the quantum and the gravitational, a physics that can describe the very beginning of the universe, a physics that can tell us what reality is made of at the deepest level. We do not have that physics yet, but we are working on it. And every step we take, every insight we gain, brings us closer. So the next time you look up at the night sky, or down at your hand, or out at the world around you, remember the Planck length. Remember that beneath the surface, beneath the atoms, beneath the quarks, there is a scale where everything changes, where space becomes foam, where time becomes discrete, where the laws of physics dissolve into something new. It is there, hidden, waiting, and it is part of you, part of everything, part of the universe. And maybe, just maybe, by understanding the Planck length, we will understand ourselves a little better. We will understand our place in the cosmos. We will understand what it means to exist, what it means to be conscious, what it means to wonder, because we are made of the same stuff as the stars. We are made of the same quantum foam. We are the universe, looking at itself, trying to figure itself out. And that is the greatest mystery of all. Thank you for joining me on this journey to the edge of the knowable. If you have thoughts, questions, or your own reflections on the Planck length and the nature of reality, I would love to hear them in the comments below. And as always, stay curious, keep wondering, keep exploring, because the universe is vast and strange and beautiful, and there is always more to discover. Until next time, this is Cosmic Drift, reminding you that even in the smallest things, there is infinite wonder. Word count 2500. Let us take a moment to truly appreciate just how small the Planck length really is. We have talked about numbers, about powers of 10, about ratios, but sometimes numbers alone cannot capture the strangeness of scale. So let us try a few more ways to wrap our minds around this impossibly tiny distance. Imagine you are holding a grain of sand, a single grain. It is small, but you can see it. You can feel it between your fingers. Now imagine that grain of sand is actually the size of the entire observable universe. Every galaxy, every star, every planet, all contained within that grain. If you were to look at that universe-sized grain of sand and try to find something the size of the original grain of sand within it, you would be looking at something about the size of a Planck length. That is the scale we are dealing with. The Planck length compared to a grain of sand is like a grain of sand compared to the entire cosmos. Here is another way to think about it. Take a single proton, one of the particles in the nucleus of an atom. A proton is already unimaginably small. You could fit about 1,000,000 trillion protons across the width of a human hair. But the Planck length is to a proton what a proton is to a distance of about 100 million kilometers. That is roughly the distance from the Earth to the Sun. So if you scaled a proton up to the size of the distance between Earth and Sun, the Planck length would still be the size of a proton. The scale is almost absurd. Or think of it this way. If you could somehow magnify an atom to the size of the entire Milky Way galaxy, which is about 100,000 light years across, the Planck length on that same scale would be about the size of a small tree. An atom blown up to galactic proportions, and the Planck length is still just a tree. These comparisons help us understand that the gap between the Planck length and the everyday world is vastly, vastly larger than the gap between the everyday world and the cosmos. This extreme smallness is not just a curiosity. It tells us something deep about the structure of reality. It tells us that there are layers upon layers of scale in the universe, and that each layer operates by different rules. The rules that govern galaxies do not apply to atoms, and the rules that govern atoms do not apply at the Planck scale. We live in a universe of nested realities, each one stranger than the last. Now let us return to the measurement problem. Why can we not just build a better microscope and look at the Planck length directly? Why is this a fundamental limit and not just a technological challenge? The answer lies in the relationship between energy and distance. To see something small, you need to probe it with something even smaller. In the world of physics, that means using particles or waves with very short wavelengths. The shorter the wavelength, the smaller the details you can resolve. This is why electron microscopes can see much smaller things than optical microscopes. Electrons have much shorter wavelengths than visible light. But here is the catch. The shorter the wavelength, the higher the energy. This is a fundamental relationship in quantum mechanics. Energy and wavelength are inversely related. If you want to probe something at the Planck length, you need a wavelength of about 1 Planck length, and that requires an enormous amount of energy. Specifically, it requires about 1 Planck energy, which is roughly 10 to the power of 19 giga-electron volts. That is about the energy of a car moving at highway speed, concentrated into a single subatomic particle. Now, what happens when you concentrate that much energy into such a tiny space? According to Einstein's theory of general relativity, energy curves spacetime. The more energy you pack into a small region, the more spacetime curves. And if you pack enough energy into a small enough space, spacetime curves so much that it collapses into a black hole. This is exactly what would happen if you tried to probe the Planck length. The very act of measurement would create a tiny black hole, and that black hole would swallow up whatever you were trying to measure. This is not a limitation of our technology. It is a limitation of the universe itself. The Planck length represents a boundary where the act of observation fundamentally alters what you are trying to observe. It is as if the universe has a built-in privacy screen at the smallest scales. You cannot peek behind the curtain without destroying the curtain. This brings us to one of the deepest problems in modern physics, the conflict between quantum mechanics and general relativity. These two theories are the pillars of 20th century physics. Quantum mechanics describes the behavior of particles and forces at the smallest scales. General relativity describes gravity and the curvature of spacetime at the larger scales. Both theories have been tested extensively, and both have passed every test with flying colors. But they are fundamentally incompatible with each other. Quantum mechanics is built on the idea that certain quantities, like energy and momentum, come in discrete packets. It is a probabilistic theory. It tells you the likelihood of finding a particle in a certain place, but not the exact location until you measure it. It treats space and time as a fixed background, a stage on which particles perform their quantum dance. General relativity, on the other hand, is a deterministic theory. It tells you exactly how space-time will curve in response to mass and energy. But in general relativity, space and time are not a fixed background. They are dynamic. They bend and stretch and warp. Space-time itself is part of the physics, not just the stage. At everyday scales, and even at the scales of stars and galaxies, this incompatibility does not matter. Quantum effects are negligible when dealing with large objects, and gravitational effects are negligible when dealing with individual particles. But at the Planck scale, both quantum effects and gravitational effects are strong, and that is where the two theories collide. Imagine trying to describe the curvature of spacetime at a scale where spacetime itself is fluctuating wildly due to quantum effects. Imagine trying to apply quantum mechanics to a situation where the background spacetime is not fixed, but is itself part of the quantum system. The math breaks down. The equations give nonsensical answers. Infinities pop up everywhere. This is the problem of quantum gravity. Physicists have been working on this problem for decades. There are several approaches, each with its own strengths and weaknesses. String theory is one of the most famous. It proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. These strings are about a Planck length in size. Different vibration patterns correspond to different particles. An electron is one pattern, a quark is another, a photon is yet another. String theory is elegant and mathematically rich. It naturally incorporates gravity. In fact, one of the vibration patterns of a string corresponds to the graviton, the hypothetical particle that carries the gravitational force. String theory also requires extra dimensions of space, not just the 3 dimensions we experience, but possibly 6 or 7 more, all curled up at scales too small to detect. These extra dimensions are necessary for the math to work out. But string theory has a problem. It makes very few testable predictions. The energies required to directly test string theory are far beyond what any particle accelerator can achieve. We would need a collider the size of the solar system to reach Planck scale energies. So string theory remains, for now, a beautiful mathematical framework without direct experimental confirmation. It is a candidate for a theory of quantum gravity, but not yet a proven one. Loop quantum gravity takes a different approach. Instead of replacing particles with strings, it focuses on the structure of spacetime itself. Loop quantum gravity suggests that spacetime is not continuous, but is made up of discrete loops or networks. These loops are woven together to form the fabric of space. The size of these loops is, you guessed it, about 1 Planck length. In loop quantum gravity, space is quantized. It comes in minimum units, just like energy comes in quanta. You cannot have half a loop, just as you cannot have half a photon. This means that space is fundamentally grainy at the smallest scales. It is like a fabric woven from threads, rather than a smooth sheet. Loop quantum gravity has the advantage of being more directly connected to general relativity. It does not require extra dimensions, but it also has challenges. It is difficult to extract predictions from the theory that can be tested experimentally, and it is not yet clear how to fully incorporate the other forces of nature, like electromagnetism and the nuclear forces, into the framework. There are other approaches as well: causal set, theory, asymptotic safety, emergent gravity, and more. Each offers a different perspective on the problem of quantum gravity. Each has its own insights and its own difficulties. The truth is, we do not yet know which approach, if any, is correct. We are still searching for the right way to think about the Planck scale. But even without a complete theory, we can explore the implications of what we do know. And one of the most fascinating implications is the idea of Planck units. Max Planck realized that by combining fundamental constants of nature, he could define a system of units that did not depend on human conventions. These are the Planck units. We have already talked about the Planck length, but there is also Planck time, which is the time it takes light to travel 1 Planck length. It is about 5.4 times 10 to the power of negative 44 seconds. That is an unimaginably short duration. In 1 second, there are more Planck times than there have been seconds since the Big Bang. Planck time represents the shortest meaningful interval of time. Below that, the concept of time itself may not make sense. Then, there is Planck mass. This one is surprising. The Planck mass is about 22 micrograms. That is tiny by everyday standards, but it is enormous compared to the mass of elementary particles. An electron has a mass of about 10 to the power of negative 30 kilograms. The Planck mass is about 10 to the power of negative 8 kilograms. That is about the mass of a flea egg. Why is the Planck mass so much larger than particle masses? It is because gravity is so much weaker than the other forces. To make gravity strong enough to matter at the quantum scale, you need a relatively large mass. The Planck energy is the energy equivalent of the Planck mass, according to Einstein's famous equation: energy equals mass times the speed of light squared. The Planck energy is about 2 billion joules. That is roughly the energy in a tank of gasoline, concentrated into a single particle. That energy would be enough to create a black hole. And then there is Planck temperature. This is the temperature at which the thermal energy of particles reaches the Planck energy. It is about 10 to the power of 32 degrees Kelvin. That is incomprehensibly hot. For comparison, the core of the Sun is about 15 million degrees Kelvin. The Planck temperature is about a million trillion times hotter than that. At the Planck temperature, all the forces of nature would be unified. Particles would have so much energy that distinctions between them would blur. The universe was at this temperature during the Planck epoch, the first tiny fraction of a second after the Big Bang. These Planck units are not arbitrary. They are built from the fundamental constants of nature: the speed of light, which sets the maximum speed of information; the gravitational constant, which sets the strength of gravity; the reduced Planck constant, which sets the scale of quantum effects; and the Boltzmann constant, which connects temperature to energy. By combining these constants in the right way, you get the Planck units. They represent the natural scales of the universe, the scales at which all the fundamental forces and principles come together. Now let us think more carefully about what it would mean for space to be grainy or pixelated at the Planck scale. We are used to thinking of space as smooth and continuous. You can always divide a distance in half, and then in half again, forever. But if space is quantized, this is not true. There would be a smallest possible distance, and you could not go smaller. Imagine a computer screen. From a distance, it looks smooth. But if you get close enough, you can see the individual pixels. Each pixel is a discrete unit. You cannot have half a pixel. The image is built up from these tiny indivisible squares. If space is quantized, it would be similar. At the Planck scale, space would be made of discrete units, like pixels. You could not zoom in any further. But space is three-dimensional, not two-dimensional like a screen. So the pixels of space would actually be tiny volumes, not squares. These volumes would be about 1 Planck length on each side. The volume of one of these units would be about 1 Planck volume, which is a Planck length cubed. That is about 4 times 10 to the power of negative 105 cubic meters. It is so small that there are more Planck volumes in a single proton than there are protons in the observable universe. If space is made of these discrete units, what does that mean for motion? When you move, you are not gliding smoothly through space. You are hopping from one unit to the next. But these hops are so small and so fast that they appear continuous to us. It is like watching a movie. A movie is actually a series of still images shown one after another, but they are shown so quickly that your brain perceives smooth motion. If space is quantized, motion would be similar. A series of discrete jumps that appear smooth because the jumps are so tiny. This has implications for the nature of time as well. If space is quantized, then time is probably quantized too. Time would come in discrete ticks, each one lasting about 1 Planck time. The universe would not be a smooth flow, but a series of snapshots, one after another, like frames in a film. Between the frames, there would be no time, no change, no motion, just a gap. But the frames would come so quickly that we would never notice the gaps. This idea challenges our intuition. We think of time as flowing smoothly, like a river. But maybe time is more like a series of still photographs, flipping by so fast that they create the illusion of flow. This is one of the strange possibilities that emerges when we take the Planck scale seriously. The uncertainty principle also takes on new meaning at the Planck scale. The uncertainty principle, discovered by Werner Heisenberg, says that you cannot know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you know the other. This is not a limitation of measurement. It is a fundamental property of nature. At the Planck scale, the uncertainty principle becomes extreme. If you try to pin down the position of a particle to within 1 Planck length, the uncertainty in its momentum becomes enormous. So enormous that the energy associated with that momentum would be enough to create a black hole. In other words, the uncertainty principle itself prevents you from measuring anything smaller than the Planck length. It is as if nature has built-in protection against probing too deeply. There is also an uncertainty relationship between energy and time. The more precisely you try to measure the energy of a system, the longer you have to observe it. If you try to measure energy over a time interval shorter than the Planck time, the uncertainty in energy becomes larger than the Planck energy. Again, you run into black holes. The uncertainty principle and the Planck scale are intimately connected. They both point to fundamental limits on what can be known and measured. This brings us to some deep philosophical questions. What does it mean for there to be a smallest length? Does it mean that space is not infinitely divisible? Does it mean that space is not really continuous, but discrete? And if space is discrete, what is it made of? What are the pixels of space? Are they physical objects, or are they just mathematical abstractions? Some physicists think that space is not a fundamental thing at all. They think that space is emergent, that it arises from something deeper. Just as temperature emerges from the motion of molecules, space might emerge from some more fundamental quantum process. In this view, asking what space is made of is like asking what temperature is made of. It is the wrong question. Temperature is not made of anything. It is a property of a collection of particles. Similarly, space might be a property of some underlying quantum system. This is a radical idea. For thousands of years, humans have thought of space as the container in which things happen, the stage on which the universe plays out. But maybe space is not the stage. Maybe space is part of the play. Maybe space is something that emerges when you have the right kind of quantum entanglement or the right kind of information structure. This is an active area of research, and we do not yet have definitive answers. But the questions themselves are profound. Let us think more about virtual particles and the quantum foam. We mentioned earlier that empty space is not really empty. It is filled with virtual particles that pop in and out of existence. But what does this really mean? And how do we know it is true? Virtual particles are a consequence of the uncertainty principle. Because energy and time are related by an uncertainty relation, it is possible for energy to fluctuate over short time intervals. A pair of particles, one matter and one antimatter, can spontaneously appear out of the vacuum as long as they annihilate each other quickly enough. The more energy the particles have, the shorter they can exist. At the Planck scale, these fluctuations are enormous. We cannot see virtual particles directly. They exist for too short a time, but we can see their effects. One of the most famous effects is the Casimir effect. If you place two metal plates very close together in a vacuum, they will attract each other. This is not due to gravity or electromagnetism. It is due to virtual particles. The space between the plates is so small that only certain virtual particles can fit. Outside the plates, all virtual particles can exist. This creates a pressure difference, and the plates are pushed together. The Casimir effect has been measured in the lab. It is real, and it is evidence that the vacuum is not empty. Another effect is the Lamb shift. This is a tiny difference in the energy levels of electrons in a hydrogen atom. The difference cannot be explained by classical physics or even by simple quantum mechanics. But it can be explained. if you take into account the virtual particles that surround the electron. These virtual particles slightly alter the electromagnetic field that the electron experiences, and this changes its energy. The Lamb shift has been measured with incredible precision, and it matches the predictions perfectly. Again, this is evidence for virtual particles. So the quantum foam is not just a theoretical idea. It has real, measurable consequences. The vacuum is a seething sea of activity. Particles and antiparticles are constantly being created and destroyed. Energy is constantly fluctuating. At the Planck scale, these fluctuations are so large that space-time itself becomes unstable. The smooth fabric of space is replaced by a chaotic, foaming structure. This is the quantum foam. Now, what about vacuum energy? If the vacuum is full of virtual particles, then it must have energy. And if it has energy, then according to general relativity, it should curve space-time. In fact, when you try to calculate the energy of the vacuum using quantum field theory, you get an absurdly large number. You get something like 10 to the power of 120 times larger than what we observe. This is called the cosmological constant problem, and it is one of the biggest unsolved problems in physics. The cosmological constant is related to dark energy, the mysterious force that is causing the expansion of the universe to accelerate. Observations tell us that dark energy exists and that it has a very small but non-zero value. But theory predicts a value that is enormously larger. Why is the vacuum energy so much smaller than we expect? No one knows. Some physicists think that there is a mechanism that cancels out most of the vacuum energy, leaving only a tiny residue. Others think that our understanding of quantum field theory or general relativity is incomplete. It is a mystery, but the fact that vacuum energy is related to the Planck scale is significant. It suggests that whatever is happening at the Planck scale has consequences for the entire universe. The smaller scales and the larger scales are connected. The quantum foam and the expansion of the cosmos are part of the same story. Let us explore a bit more about the different theories of quantum gravity and what they tell us about the Planck scale. We have mentioned string theory and loop quantum gravity, but there are other ideas worth considering. One approach is called causal set theory. This theory proposes that space-time is fundamentally discrete, made up of individual events or points. These points are related to each other by causal connections. One event can influence another if there is a causal link between them. The structure of space-time emerges from the network of these causal relationships. In causal set theory, the Planck scale sets the density of these points. There is roughly 1 point per Planck volume. This theory is elegant in its simplicity, but it is still in the early stages of development. Another idea is asymptotic safety. This approach tries to make general relativity work at the quantum level by finding a special point in the space of possible theories where the theory becomes well behaved. At this point, the infinities that usually plague quantum gravity disappear. Asymptotic safety does not require extra dimensions or new fundamental objects. It works with the same space-time and fields that we already know, but it requires that gravity behaves in a very specific way at high energies. Whether this is true is still an open question. There is also the idea of emergent gravity. This is the notion that gravity is not a fundamental force, but an emergent phenomenon, like temperature or pressure. Just as temperature emerges from the motion of molecules, gravity might emerge from the entanglement of quantum information. In this view, space-time itself is not fundamental. It is a kind of hologram, a projection of information stored on a distant boundary. This is related to the holographic principle, which we mentioned earlier. Emergent gravity is a radical idea, and it is still very speculative. But it has attracted a lot of attention because it offers a completely different way of thinking about the problem. Each of these approaches has its own perspective on the Planck scale. String theory sees it as the size of fundamental strings. Loop quantum gravity sees it as the size of discrete loops of space. Causal set theory sees it as the spacing between fundamental events. Asymptotic safety sees it as the scale where quantum effects of gravity become important. Emergent gravity sees it as the scale where the illusion of continuous spacetime breaks down. They all agree that the Planck scale is special, but they disagree on why. This diversity of ideas is actually a good thing. It means that physicists are exploring the problem from many angles. Eventually, experiments or observations might give us clues about which approach is correct. Or maybe the truth is some combination of these ideas. Or maybe it is something completely different that no one has thought of yet. Science is a process of exploration, and we are still in the early stages of exploring the Planck scale. Let us think about the implications of a pixelated or grainy universe in more detail. If space is made of discrete units, then there are some strange consequences. For one thing, there would be a maximum speed at which information can propagate through space. We already know that the speed of light is the maximum speed, but if space is grainy, then light would not move smoothly. It would hop from one unit of space to the next. Each hop would take 1 Planck time. So the speed of light would be 1 Planck length per Planck time. This is exactly the speed of light that we measure. So the graininess of space, if it exists, is consistent with the speed of light. But there might be other effects. If space is grainy, then particles moving through space might experience a kind of friction or drag. This would be incredibly tiny, but it might be detectable over very long distances. Astronomers have looked for such effects by studying light from distant galaxies and gamma-ray bursts. So far, they have not found any evidence of graininess. This puts limits on how grainy space can be. If space is pixelated, the pixels must be smaller than we can currently detect. They must be at or below the Planck scale. Another consequence of grainy space is that it would affect the propagation of gravitational waves. Gravitational waves are ripples in spacetime, caused by violent events like colliding black holes. If spacetime is grainy, then gravitational waves might scatter off the grains, like light scattering off fog. This would cause the waves to lose energy or change direction. Again, astronomers have looked for such effects, and so far they have not found any. This also puts limits on the graininess of space, but the absence of evidence is not evidence of absence. Just because we have not detected graininess yet does not mean it is not there. It might be that the effects are too small to measure with current technology. Or it might be that the graininess is there but does not affect light or gravitational waves in the way we expect. The search continues. There is also the question of what happens to the concept of distance at the Planck scale. In everyday life, distance is straightforward. It is the space between 2 points. But at the Planck scale, the concept of a point becomes fuzzy. If space is grainy, then a point is not infinitely small. It is at least 1 Planck length across. And if space is fluctuating due to quantum effects, then the distance between 2 points is not fixed. It is constantly changing. Distance becomes a probabilistic concept, not a definite one. This has implications for geometry. In classical geometry, you can define shapes and angles and distances with perfect precision. But in quantum geometry, everything is fuzzy. A triangle at the Planck scale would not have perfectly straight sides. Its angles would not add up to exactly 180 degrees. The rules of geometry would be different. This is one of the things that loop quantum gravity explores. It tries to understand what geometry looks like when space is quantized. Let us also think about the role of symmetry at the Planck scale. Symmetry is a powerful concept in physics. It refers to situations where something looks the same after a transformation. For example, a circle looks the same after you rotate it. A sphere looks the same from any direction. Symmetries are deeply connected to conservation laws. The symmetry of space under translations leads to conservation of momentum. The symmetry of space under rotations leads to conservation of angular momentum. The symmetry of time under translations leads to conservation of energy. At the Planck scale, some of these symmetries might break down. If space is grainy, then it is not symmetric under translations. You cannot shift by an arbitrary amount. You can only shift by multiples of the Planck length. This might mean that momentum is not perfectly conserved at the Planck scale, or it might mean that the concept of momentum needs to be redefined. Similarly, if time is grainy, then energy might not be perfectly conserved over very short time intervals. These are speculative ideas, but they show how the Planck scale challenges our basic assumptions. There is also the idea of supersymmetry, which is a symmetry between particles of different types. Supersymmetry predicts that every particle has a partner particle with different properties. These partner particles have not been observed yet, but some physicists think they might exist at very high energies, possibly near the Planck scale. If supersymmetry is real, it could help solve some of the problems in particle physics and quantum gravity, but so far, there is no direct evidence for it. Another symmetry that might be important at the Planck scale is scale invariance. This is the idea that the laws of physics look the same at all scales. If you zoom in or zoom out, the patterns repeat. Fractals are an example of scale invariance. Some physicists think that spacetime might have a fractal structure at the Planck scale. It might look rough and irregular at all scales, with no smooth limit. This is a beautiful idea, but it is also very speculative. Let us return to the philosophical implications of the Planck scale. One of the deepest questions is whether the Planck length represents a true limit on reality, or just a limit on our ability to measure reality. Is there something smaller than the Planck length, but we just cannot access it? Or is the Planck length the smallest thing that can exist? Most physicists lean toward the latter view. They think that the Planck length is not just a practical limit, but a fundamental one. Below the Planck length, the concepts of space and time break down. There is no there. It is not that we cannot measure it. It is that it does not exist in any meaningful sense. This is a profound statement. It says that reality has a bottom, that you cannot keep zooming in forever, that there is a smaller scale, and beyond that, there is nothing. But this raises another question. If space and time are not fundamental, then what is? What is the deeper reality from which space and time emerge? Some physicists think it is information, that the universe is fundamentally made of information, and space and time are just ways that information is organized. Others think it is quantum entanglement, that the connections between quantum systems are more fundamental than the systems themselves. Still others think it is something we have not even conceived of yet. These are not just abstract philosophical questions. They have implications for how we do physics. If space and time are emergent, then we need a new framework for describing the universe. A framework that does not assume space and time from the start. This is incredibly difficult. Our entire language of physics is built on the concepts of space and time. Trying to do physics without them is like trying to write a novel without using the letter E. It forces you to think in completely new ways. There is also the question of whether the universe is deterministic or probabilistic at the deepest level. In classical physics, the universe is deterministic. If you know the state of the universe at one moment, you can predict its state at any future moment. But quantum mechanics is probabilistic. It only gives you probabilities, not certainties. At the Planck scale, this probabilistic nature is extreme. The quantum foam is a realm of pure chance, where anything that can happen does happen, as long as it happens quickly enough. Some physicists think that this randomness is fundamental, that the universe is not deterministic at the deepest level, that there is true chance built into the fabric of reality. Others think that the randomness is just apparent, that there is a deeper deterministic theory underneath, and quantum mechanics is just an approximation. This is the debate between the Copenhagen interpretation and hidden variable theories. It is one of the oldest debates in quantum mechanics, and it is still not resolved. The Planck scale also raises questions about the nature of causality. Causality is the idea that causes precede effects, that the past influences the future, but not the other way around. In classical physics, causality is absolute, but in quantum mechanics, things are more subtle. Quantum entanglement allows particles to be correlated in ways that seem to defy causality. And at the Planck scale, where time itself might be grainy or even non-existent, the concept of causality becomes very murky. Some theories of quantum gravity suggest that causality might not be fundamental, that the order of events might not be fixed, that in some sense the future might influence the past, or that past and future might be on equal footing. This is a mind-bending idea. It challenges one of our most basic intuitions about how the world works, but it is a possibility that physicists are seriously considering. Let us also think about the connection between the Planck scale and consciousness. This is a controversial topic, but it is worth mentioning. Some physicists and philosophers have speculated that consciousness might be related to quantum processes in the brain, and if quantum processes are involved, then the Planck scale might be relevant. The idea is that the brain is not just a classical computer, but a quantum computer, and that consciousness arises from quantum effects. Most neuroscientists are skeptical of this idea. The brain is warm and wet, and quantum effects usually require cold and isolated systems. It is hard to see how quantum coherence could be maintained in the brain for long enough to matter. But a few researchers, like Roger Penrose and Stuart Hameroff, have proposed specific mechanisms by which quantum effects in structures called microtubules might play a role in consciousness. These ideas are highly speculative and not widely accepted, but they show how the Planck scale and quantum mechanics in general can inspire new ways of thinking about old problems. Whether or not consciousness is related to quantum mechanics, there is a deeper connection between the Planck scale and the nature of observation. Quantum mechanics tells us that observation plays a fundamental role in determining the state of a system. Before you measure a particle, it is in a superposition of states. After you measure it, it is in a definite state. This is the measurement problem, and it is one of the deepest puzzles in quantum mechanics. At the Planck scale, the measurement problem becomes even more acute. If spacetime itself is quantum, then what does it mean to observe spacetime? Who or what is doing the observing? Is there an observer outside the universe looking in? Or is the universe observing itself? These questions touch on the boundary between physics and philosophy. They remind us that science is not just about collecting data. It is about understanding the nature of reality and our place in it. Let us think about the practical implications of the Planck scale for cosmology. The Planck epoch, the first 10 to the power of negative 43 seconds after the Big Bang, is a time when the universe was so hot and dense that quantum gravity effects were dominant. During this epoch, the four fundamental forces were unified into a single force. The universe was a seething quantum foam, with no clear distinction between space and time, matter and energy. We cannot observe the Planck epoch directly. The universe was opaque to light at that time, but we can see its effects. The tiny quantum fluctuations during the Planck epoch were stretched out by cosmic inflation, and they became the seeds of the large-scale structure of the universe. The galaxies, clusters, and superclusters that we see today all trace back to those primordial fluctuations. In a very real sense, the Planck scale is written into the sky. Every time we look at the cosmic microwave background, we are seeing the fingerprints of the Planck epoch. Inflation is a theory that proposes that the universe underwent a period of exponential expansion very early on, just after the Planck epoch. During inflation, the universe doubled in size many times over in a tiny fraction of a second. This expansion smoothed out the universe and stretched quantum fluctuations to cosmic scales. Inflation explains many features of the universe that are otherwise puzzling, like why the universe is so uniform on large scales, and why it is so flat. If inflation is correct, and most cosmologists think it is, then the Planck scale played a crucial role in shaping the universe. The quantum fluctuations at the Planck scale were the seeds of everything we see. Without those fluctuations, the universe would be perfectly smooth and uniform. There would be no galaxies, no stars, no planets, no life. The Planck scale is not just an abstract concept. It is the origin of structure in the universe. There is also the question of what came before the Big Bang. Did time itself begin at the Big Bang? Or was there something before? Some theories suggest that the Big Bang was not the beginning but a transition, that the universe existed in some form before the Big Bang, and that the Big Bang was a kind of bounce or phase transition. In these models, the Planck scale is the scale at which the transition occurred. One such model is loop quantum cosmology, which is based on loop quantum gravity. In this model, the Big Bang is replaced by a big bounce. The universe contracts to a very small size, about the Planck scale, and then bounces back and expands. The quantum effects of gravity prevent the universe from collapsing to a singularity. Instead, it reaches a minimum size and then rebounds. This is a beautiful idea, and it avoids the problem of the initial singularity. But it is still speculative. We do not yet have observational evidence for a big bounce. Another idea is the multiverse. This is the notion that our universe is just one of many universes, each with its own properties. In some versions of the multiverse, new universes are constantly being created by quantum fluctuations at the Planck scale. Each universe is a bubble, and the bubbles are separated by regions of space that are still inflating. In this picture, the Planck scale is the scale at which new universes are born. It is the creative engine of the multiverse. The multiverse is a controversial idea. Some physicists love it, others hate it. The main criticism is that it is not testable. If other universes are forever beyond our reach, then how can we ever know if they exist? But proponents argue that the multiverse is a natural consequence of our best theories, like inflation and string theory. And they point out that even if we cannot observe other universes directly, we might be able to see indirect evidence, like patterns in the cosmic microwave background. Let us also consider the role of the Planck scale in black hole physics. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where the curvature of spacetime becomes infinite. But most physicists think that singularities are not real. They are a sign that our theories break down. At the center of a black hole, quantum gravity effects should become important, and the singularity should be replaced by something else. Something at the Planck scale. What that something is, we do not know. It might be a region of quantum foam. It might be a Planck scale structure, like a string or a loop. It might be a gateway to another universe. Or it might be something completely different. Understanding what happens at the center of a black hole is one of the key goals of quantum gravity research. Black holes also have a temperature, as Stephen Hawking discovered. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. The temperature of a black hole is inversely proportional to its mass. A small black hole is hot. A large black hole is cold. A black hole with a mass of 1 Planck mass would have a temperature of 1 Planck temperature. It would be incredibly hot, and it would evaporate almost instantly. Hawking radiation connects black holes to thermodynamics and information theory. It raises deep questions about what happens to information that falls into a black hole. Does it disappear forever? Or is it somehow encoded in the Hawking radiation? This is the black hole information paradox, and it is one of the most important problems in theoretical physics. The resolution of this paradox will likely require a full theory of quantum gravity, and it will likely involve the Planck scale. There is also the concept of black hole entropy. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is surprising. In ordinary thermodynamics, entropy is proportional to volume, but for black holes, it is proportional to area. This suggests that the information content of a black hole is stored on its surface, not in its interior. This is the holographic principle, which we mentioned earlier. And the fundamental units of area are Planck areas, which are Planck length squared. So the Planck scale is intimately connected to the information content of black holes. Let us think about the future of Planck scale physics. What new technologies or observations might give us insights into the Planck scale? One possibility is gravitational wave astronomy. Gravitational waves are ripples in spacetime, and they carry information about the most violent events in the universe. By studying gravitational waves, we might be able to detect effects of quantum gravity. For example, if spacetime is grainy, gravitational waves might be scattered or absorbed in ways that we can measure. Another possibility is particle physics. Although we cannot build a collider that reaches Planck scale energies, we might be able to see indirect effects. For example, if there are extra dimensions of space, as string theory predicts, then particles might be able to escape into those dimensions at high energies. This would show up as missing energy in collider experiments. So far, no such effects have been seen, but the search continues. There is also the possibility of observing quantum gravity effects in the early universe. The cosmic microwave background is a snapshot of the universe when it was only 380,000 years old. But it carries information about even earlier times, including the Planck epoch. By studying the patterns in the cosmic microwave background, we might be able to see the fingerprints of quantum gravity. This is one of the goals of future cosmology missions. Another approach is to study extreme astrophysical objects like neutron stars and black holes. These objects have incredibly strong gravitational fields, and they might provide a natural laboratory for testing quantum gravity. For example, The merger of two neutron stars produces both gravitational waves and electromagnetic radiation. By studying both signals, we might be able to learn about the behavior of matter at extreme densities, where quantum gravity effects might be important. There are also theoretical approaches. Physicists are constantly developing new mathematical tools and new ways of thinking about quantum gravity. Advances in areas like quantum information theory, holography, and tensor networks are providing new insights. These tools might help us understand the Planck scale, even without direct experimental access. Let us also reflect on the beauty and mystery of the Planck scale. There is something deeply satisfying about the idea that the universe has a natural set of units, that there are fundamental scales built into the fabric of reality. The Planck units are not arbitrary. They are determined by the constants of nature. They are the same everywhere in the universe, and they have been the same for all time. They are truly universal. There is also something humbling about the Planck scale. It reminds us of how much we do not know. We have made incredible progress in understanding the universe, from the largest galaxies to the smallest particles, but the Planck scale remains beyond our reach. It is a frontier that we have not yet crossed, and it is a reminder that there is always more to discover, always deeper mysteries to explore. The Planck scale also connects the very small to the very large. It is the bridge between quantum mechanics and general relativity. It is the scale where the forces of nature unify. It is the scale that determined the initial conditions of the universe. It is the scale that governs the behavior of black holes. The Planck scale is not just a curiosity. It is central to our understanding of the cosmos. And perhaps most importantly, the Planck scale reminds us that reality is stranger than we can imagine. The universe is not just a collection of objects moving through space and time. It is a dynamic, quantum, interconnected whole. Space and time themselves might be emergent. Causality might not be fundamental. The vacuum might be a seething foam of virtual particles. These are not science fiction ideas. They are serious scientific hypotheses, grounded in our best theories and observations. As we continue to explore the Planck scale, we are not just learning about physics. We are learning about the nature of reality itself. We are learning about the limits of knowledge. We are learning about the relationship between the observer and the observed. We are learning about the deep connections between mathematics and the physical world. These are profound questions, and the Planck scale is at the heart of them. So the next time you think about the universe, remember the Planck length. Remember that beneath the world of atoms and particles, there is another world. A world of quantum foam and fluctuating space-time. A world where the rules are different. A world that we are only beginning to understand. It is a world that is part of you, part of everything, part of the cosmos. And it is waiting to be explored.